As we continue to develop and refine our neural networks, it is essential to understand two common pitfalls: overfitting and underfitting. These can significantly impact your model's performance, so let's look at them in more detail. Overfitting occurs when a model learns not just the underlying patterns of a dataset, but also its noise and specific details that don't generalize well. It's like memorizing every detail of a book, but not understanding its overall message. The result is a model that performs well in training, but not on the validation or test sets. The model will be unreliable in practical applications. Underfitting happens when a model is too simple to capture the underlying patterns of a dataset. This could be because it doesn't have enough layers or neurons, or it hasn't been trained on enough epochs. The result is a model that performs poorly on all datasets because it just hasn't learned enough from the data. Underfitting indicates that the model lacks the complexity needed to make accurate predictions. It just doesn't have the tools to do the job properly. To identify overfitting, look for a model that performs well on training data, but shows a significant drop in performance on validation data. Conversely, underfitting can be recognized when your model performs poorly on both training data and validation sets, indicating that it just hasn't captured the necessary patterns. Solving a problem is as important as spotting it. One method of preventing overfitting is to simplify the model, reducing the number of layers or neurons. More complex methods include regularization, dropout, and early stopping. Regularization involves applying a penalty to the model when it relies too heavily on any particular piece of information. Level 1 regularization encourages the model to completely ignore some less important information, making the model simpler. Level 2 regularization discourages the model from putting too much importance on any one thing, leading to a more balanced and generalizable model. These techniques prevent the model from becoming too tailored to the training data. Dropout prevents overfitting by randomly dropping or turning off a proportion of the neurons during training. This forces the neural net to recognize more prominent features of the data through more distributed representations and reduces the chance of it becoming too reliant on a specific network architecture. Early stopping is when you monitor a model's performance on the validation set and stop training when this starts to deteriorate rather than improve. It's like realizing that you should stop studying for a test when you start to memorize the example answers instead of actually understanding the subject. Avoiding underfitting is simpler, but can often be more costly. Increasing the complexity of your model may involve adding more layers or neurons, which increases the learning capacity. You can also allow for more epochs, giving more opportunity to recognize the patterns in the training data. You may also be able to improve feature selection, ensuring the model has access to the most relevant data features. Understanding and addressing overfitting and underfitting are critical steps in building effective neural networks. By balancing model complexity and training duration, and using techniques such as regularization and dropout, you can create models that generalize well and perform reliably in real-world scenarios. Without them, you run the risk of an unusable model.